Gravity. It's the ultimate cosmic glue. This invisible force is everywhere all the time. It keeps your feet firmly on the ground. It holds the moon in a graceful dance around Earth. It even commands the stars in their galaxies, and galaxies in their colossal clusters. Without gravity, our universe as we know it simply wouldn't exist. It's fundamental. Humans have always wondered about this persistent pull. Ancient astronomers tracked the planets, marveling at their predictable paths. Philosophers pondered why objects invariably fall downwards. Understanding gravity unlocks many of the universe's secrets. From the smallest pebble to the largest supercluster of galaxies, gravity writes the rules of interaction. Prepare to understand the force that literally shapes your world and the entire cosmos. Enter Sir Isaac Newton, a monumental figure in the history of science. He lived in the 17th century, a time of great intellectual awakening. You've probably heard the story about an apple falling from a tree. While it might not have been a single aha moment, that falling apple symbolized a profound insight about the universe. Newton didn't discover gravity. People were quite aware that things fell. What Newton did was revolutionary. He realized that the force pulling that apple to the ground was the force keeping the moon in orbit around the Earth. It was a universal principle, acting everywhere, on everything. This was a cosmic connection nobody had made before. He showed us that the universe isn't arbitrary. It follows predictable mathematical laws. Newton laid out his groundbreaking work in his book, Philosophiae Naturalis Principia Mathematica. Science was never the same. So what is this gravitational force all about? It starts with mass. Mass isn't your weight. Weight changes depending on where you are. Mass is the amount of stuff, the atoms, the matter that makes up an object. And here's the kicker. Every single object that has mass exerts a gravitational force. You, me, this planet, the sun. The more mass an object possesses, the stronger its gravitational pull. Think about it. A bowling ball has more mass than a tennis ball. So the bowling ball has a stronger gravitational influence, though it's tiny on a human scale. The Earth, with its enormous mass, has a significant gravitational pull. This principle extends to the grandest scales. Our sun is vastly more massive than Earth. Its immense gravity holds all the planets, asteroids, and comets of our solar system in their orbits. Let's dig a little deeper into this mass-gravity relationship. Newton's law tells us something very specific. The gravitational force between two objects is directly proportional to the product of their masses. That means if you double the mass of one object, the gravitational force between them also doubles. Simple, elegant. Now what if you double the mass of objects? The force doesn't just double, it quadruples. 2 times 2 equals 4. This multiplicative effect is crucial. It shows how quickly gravitational forces can ramp up when you're dealing with truly massive celestial bodies. It's a cosmic multiplier effect. More particles, more stuff, means a stronger collective tug. The combined effort becomes immense when you have astronomical amounts of mass. This direct link between mass and gravitational strength explains the universe's heavyweights. Section 5. The distance dilemma. Gravity's fading embrace. Mass isn't the only player in this gravitational game. Distance matters, a lot. The gravitational force between two objects isn't constant, it changes depending on how far apart they are. And the rule is quite straightforward. As the distance between two objects increases, the gravitational force between them decreases. Think of it like the light from a campfire. When you're close, it's bright and warm. As you walk away, the light dims, its intensity fades. Gravity behaves in a similar way. Its influence weakens over distance. It still reaches out across the vastness of space, but its grip loosens. This balance between reach and strength is fundamental to the structure we observe in the cosmos. It's a cosmic balancing act. Section 6. The inverse square law, why closer is stronger. Newton didn't just say gravity weakens with distance, he told us exactly it weakens. It follows something called the inverse square law. Now, inverse square law might sound a bit intimidating, but the concept is quite beautiful in its simplicity. It means the force decreases with the distance. Let's break that down. If you double the distance between two objects, the gravitational force between them doesn't just halve, it becomes 1/4 as strong. If you triple the distance, the force drops to 1/9 of its original strength. It weakens rapidly as objects move apart. This rapid fall-off is incredibly important. The inverse square law sculpts the cosmos on all scales. Section 7. Cosmic Calculations, Newton's Gravitational Recipe. Newton gave us more than concepts, he gave us an equation. This equation is a cornerstone of classical physics and has been used for centuries to understand the forces that govern the universe. A recipe to calculate the gravitational force between any two objects in the universe. This simple yet profound equation has allowed scientists to predict the behavior of planets, stars, and even galaxies. It looks like this. F equals g times m1 times m2 divided by r squared. This formula encapsulates the essence of gravitational interaction. Here F is the gravitational force we want to find. It's the force that pulls objects towards each other, whether they are apples falling from trees or planets orbiting stars. Simple enough, right? Let's look at the ingredients. Each part of this equation plays a crucial role in determining the gravitational force. M1 and M2 are the masses of the two objects. These masses determine how much gravitational pull each object exerts on the other. We talked about mass, more stuff, more pull. The greater the mass, the stronger the gravitational attraction. Then there's R, which is the distance between the centers of the two objects. The farther apart the objects are, the weaker the gravitational force. And G is the gravitational constant. This constant is a key part of the equation, ensuring that the units and scale of the force are correct. It's a tiny number, about 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. Despite its small size, it has a huge impact on the calculations. This tells us gravity is inherently weak unless huge masses are involved. For example, the gravitational pull between the Earth and the Moon is significant because of their large masses. Let's try a quick calculation. By applying Newton's equation, we can understand the gravitational forces at play in everyday scenarios. What's the gravitational force between the Earth and a 70-kilogram person on its surface? This example will help us see the equation in action. Earth's mass, m1, is about 5.97 times 10 to the 24th kilograms. This massive number reflects the enormous size of our planet. The person's mass, m2, is 70 kilograms. This is a typical mass for an average adult human. Plugging these into F equals 6.674 times 10 to the negative 11 times 5.97 times 10 to the 24th times 70, divided by 6.37 times 10 to the 6th squared. This calculation will reveal the gravitational force between the Earth and the person. Section 8. Gravity all around us. From tides to galaxies. Gravity is a force that shapes our universe, influencing everything from the smallest particles to the largest galaxies. Newton's law isn't just for astronomers and physicists, it's a fundamental principle that governs the motion of objects in our everyday lives. Its effects are all around you, every moment of every day. From the way we walk to the way water flows, gravity is at work. The most obvious one? Things fall down. This simple observation led to profound discoveries about the nature of our world. Drop your keys and gravity pulls them to the floor. It's a force we often take for granted, yet it's always there, working tirelessly. This constant downward tug is Earth's mass calling out to the mass of your keys. It's reliable and predictable, a force we can always count on. Then there are the tides. These rhythmic movements of the ocean are a direct result of gravitational forces at play. The rhythmic rise and fall of ocean waters. It's a dance choreographed by the gravitational pull of celestial bodies. This is mainly due to the Moon's gravitational pull. The Moon's influence on Earth is a powerful reminder of the interconnectedness of our universe. The side of Earth closer to the Moon gets pulled a bit harder, creating a bulge of water. This bulge is what we experience as high tide. The far side gets pulled less, creating another bulge. This results in 2 high tides and 2 low tides each day. The Sun also plays a role, creating even higher tides when aligned with the Moon. And what about orbits? The gravitational dance extends beyond our planet. Why do planets go around the Sun and moons around planets? It's a beautiful balance of forces, a cosmic ballet. An object in motion wants to continue in a straight line. That's inertia. But in the vastness of space, gravity has the final say. But gravity constantly pulls it towards the central body. This delicate balance keeps planets in orbit, creating the dynamic and ever-changing universe we observe. Section 9. Conclusion, our universe, bound by gravity. So, there you have it. Gravity. It's the force that keeps our feet firmly planted on the ground and the planets in their orbits. It's not just some abstract concept, it's a tangible force that we can observe and measure in our everyday lives. It's a fundamental force of nature, as described by Isaac Newton's elegant law. His work laid the foundation for our understanding of how objects interact. We've seen that its strength depends on the mass of objects. More mass means more gravitational pull. This is why planets can hold moons in their orbits. And it depends on distance, weakening rapidly the farther apart objects are, following the inverse square law. This explains why distant stars don't affect us as much as our own sun. Newton's insight was truly profound. He connected the motion of celestial bodies with the fall of an apple. He gave us a universal framework, connecting the everyday fall of an apple to the majestic orbits of planets. This was a revolutionary idea at the time. His law of universal gravitation was a cornerstone of classical physics for centuries. It stood the test of time and guided countless discoveries. It empowered us to predict, to explore, and to understand our cosmic neighborhood in ways never before possible. Telescopes and space missions owe much to this understanding. Understanding gravity connects us to the universe. It allows us to comprehend the vastness and the intricate dance of celestial bodies. It reveals the invisible tethers that bind matter together, from the smallest scales to the unimaginably large. Gravity is the glue of the cosmos. This invisible force, gravity, orchestrates the universe's magnificent ballet. It ensures that everything moves in harmony. The universe is bound by gravity, and we are bound to explore it. Our journey to understand this force is far from over.